Example 9, the series n equals 1 to infinity of 1 over n squared plus 1. So step 1 is to check that it is continuous, positive, and decreasing. So I have 1 over x squared plus 1 in my calculator, and here's my graph. And again, I'm only looking, this starts at n equals 1, so I'd be starting here. It is continuous. All the values are above the x-axis, so that makes it positive. And then it is decreasing, so we meet our criteria. The next step is to write this as an improper integral. So the integral from 1 to infinity of 1 over x squared plus 1 dx. We write that with a limit as r goes to infinity of the integral from 1 to r of 1 over x squared plus 1 dx. And that is arctangent. So I get the limit as r goes to infinity of arctan of x evaluated from 1 to r, which is going to give me the limit as r goes to infinity of arctan of r minus arctan of 1. Okay, so arctan of 1 is going to be pi over 4. You can always put that in your calculator and test that out. And the limit, you can look at the graph to get this, but that limit is pi over 2. So get pi over 2 minus pi over 4 gives me pi over 4. So this integral converges. And now I just need to do my write-up. My write-up is going to be since f of x equal to 1 over x squared plus 1 is continuous, positive, and decreasing, and the integral from 1 to infinity of 1 over x squared plus 1 dx converges. Therefore, the sum from n equals 1 to infinity of 1 over n squared plus 1 converges by IT, so by the integral test. And that is the write-up for that one. Okay, and then we're going to go ahead and flip to the top of the next page. So I have this series from n equals 2 to infinity of 1 over the quantity n times natural log of n. My first step is to check that it is continuous, positive, and decreasing. So let me put that into my calculator here. So 1 divided by x times natural log of x. Okay. So I graph that. And notice that this one starts at 2. So this is x equals 1. Here's x equals 2. So from 2 on, this is continuous. It's all above the x-axis, and it is decreasing. So I meet all 3 of my criteria here. Check those off. And now I need to look at integrating this. So I have the integral from 2 to infinity of 1 over x ln of x dx, which is going to be equal to the limit as r goes to infinity of the integral from 2 to r of 1 over x ln of x dx. And now I need to find the antiderivative. So this is going to be a u sub. So I'm going to let u be ln of x, which means du is 1 over x dx. Okay. And let's see, so I'm going to do this off to the side as an improper integral because I don't want to deal with the bounds and the limits and all of that. So I have the integral of 1 over x ln of x dx is equal to the integral of 1 over u du. And that antiderivative is ln of u. And it's going to be ln of x, which is kind of crazy. So I have my antiderivative. So this limit now is going to be equal to the limit as r goes to infinity of ln of x from 2 to r, which is equal to the limit as r goes to infinity of ln of r minus ln of 2. ln of r is going to infinity slowly, but it is definitely going to infinity, so this integral diverges. And now all that's left is my write-up. Since f of x equal to 1 over x ln of x is continuous, positive, decreasing, and the integral from 2 to infinity of 1 over x ln of x dx diverges. Therefore, the series n equals 2 to infinity of 1 over n ln of n diverges by it. Okay, so that is your conclusion statement.